So today in this class we will discuss the important topics from the chapter solutions, and we will discuss some more past paper questions as well. Okay. So first let us go through the important equations, the topics from the same chapter solutions. Okay. So I hope the screen is visible. So let us go to the topic solutions. So first of all, we have to know what are different kinds of solutions. So we have three different types of solutions. They are gaseous solutions, liquid solutions, and solid solutions. So in these three solutions as well, based on the solute and solvent, we can classify them because every solutions are made up of two components, right? They are solute and solvent. So based on the solute, different kinds of solute and solvents we are using, we will get different types of solutions. So we have to know the type of solutions and the examples as well. For example, if it is solute solvent is like gas solution, the oxygen and nitrogen gas mixture is a best example. So those kind of examples also we have to know. Then coming to the solid solutions, we have again three types, right? So in case of gaseous solutions, the solvent will be always gas and the solute will change, like it will be gas or liquid or solid. And coming to the liquid solutions, the solvent will be liquid and the solute will again change. If you come into the solid solutions, the solvent will be the solid and the solute will be again different. So this is the classifications. Okay. Now the another important thing is Henry's law. So we have to know what is Henry's law and which is the equation to represent the Henry's law. So according to Henry's law, the mass of a gas dissolved per unit volume of a solvent is proportional to the pressure of the gas at constant temperature. So this is called Henry's law simply. So for NEET, we doesn't need any definitions or anything, but we have to know the equations and important factors which affects the different kind of different parameters, those kind of things we have to know. So here in case of Henry's law, we have to know the equations. So for Henry's law, we can predict in like we have two equations. The first one is like the partial pressure of the gas will be the product of Henry's constant and the mole fraction of the gas in the solution. So that is P is equal to Kh into mole fraction. Here Kh will be the Henry's constant. So this is the first thing. Now we can simply say this mole fraction. Mole fraction is a method to express the concentration, right? So what the mole fraction denotes how much gas is soluble in the solution. So we can use the term solubility as well. So we can write in two ways. First one, Henry's constant times the mole fraction, or Henry's constant times the solubility. So this is the equation to find out the partial pressure of the gas. Okay, this is according to the Henry's law. Okay, then the next thing we have to know, that is how the solubility is depending, what are the different factors affecting the solubility. So we know that from this previous equation we can say the partial pressure of the gas is directly proportional to mole fraction, right? That is partial pressure is proportional to the mole fraction of the gas. Now if you check the relationship between the Henry's constant and mole fraction, that will be inversely proportional to each other. That is, the Henry's constant is inversely proportional, means when the solubility of the gas is increasing, the Henry's constant will decreases. That is the another relationship. Now if you check the solubility and temperature relationship, when temperature is increasing, the solubility of the gas is decreasing. So this is all related to the solubilities of the gases only. Okay, so in terms of gas, when temperature is increasing, the solubility of the gas in a particular liquid solution is decreasing. So these are another important relationship to remember. Okay, so now this is a graphical representation. Here we can see in the x-axis we have mole fraction of hydrochloric acid in its solution in cyclohexane. So here HCl we have in gaseous state, and here in the y-axis we have the partial pressure. So we know that the partial pressure and the mole fractions are directly proportional, right? From the Henry's law, we got that the partial pressure is directly proportional to the mole fraction. So when the mole fraction of the gas is increasing, obviously the partial pressure will also increases. That's why we are getting a straight line passing through the origin. Okay, this is how we are explaining the Henry's law, and we need to know these relationships to find out the special, like if they are asking for any parameters, if they're asking some problems, we have to know these relationships. Okay, that is the thing. Now, the next one, we have different methods to express the concentrations of the solutions, right? So we have to know all the methods, and we have to know what is the expression for different terms. Like in order to express the concentration, we have mass percentage, volume percentage, mass by volume percentage, parts per million, then mole fraction, molarity, okay, normality. So for all these, we have to know their equations to calculate these particular parameters. Like what are the different types of methods to express the concentration. So we have to know that. Okay. So mass percentage means we can calculate by using this equation. That is, mass percentage of a component will be equal to the mass of the particular component. Suppose we have a solution. So that solution is containing, suppose two solutes are present. So what is the mass percentage of the components? So suppose we have two components A and B. So I have to know the mass percentage of the component A. So whatever the mass of the component A in that solution divided by the total mass of the solution times 100. This is the equation. Okay, so the total mass will be the mass of the total solution. But the first one, that is the mass of the component, means that will be the whatever the component you have to find out the mass percentage, that one. So the mass percentage of A in this mixture will be equal to the mass of A divided by the total mass times 100. Okay, suppose if you want to find out the mass percentage of component B, that will be mass of B dissolved in the solution divided by total mass times 100. This is the thing. Okay, similarly, we have one more method to express the concentration, that is volume percentage. So coming to the volume percentage, similar to that of the mass percentage. So in the mass percentage, we have used the mass of the component, but in volume percentage, we will use the volume of the component. The same. Suppose A and B are the two components dissolved, means they are liquids or whatever. So they are prepared, the solution is prepared. So what is the volume percentage of A? So that will be the volume of A divided by the total volume of the solution times 100. The same thing. Okay. Now we have mass by volume percentage. So that will be the whatever the, suppose I have to find out the mass by volume percentage of A. So that is equal to the mass of the solute A divided by total volume of the solution times 100. So it is like whatever the quantity we have to find out, based on that we have to change the quantities that we are taking here. Okay, then another one is parts per million or ppm. So parts per million is actually, it is used to express minor, very minor concentrations. Okay, for example, the suppose if you want to find out the amount of, suppose a particular pollutant in the atmosphere, we are using the ppm. So ppm is helpful to express the minute concentrations. Okay, so here parts per million, we have an equation, that is the number of parts of the component divided by total number of all the components times 10 to the power 6. This is the equation. Okay, so these are the important equations that we have. Now coming to the mole fraction. Okay, so mole fraction is very important. So because in the NEET papers we can see there are many questions from this mole fraction topic. So mole fraction means, suppose I have a solution of A and B, same as we discussed in the previous case, A and B. So they are mixed together to produce a solution. So my question is, what is the mole fraction of A in the solution? So it will be mole fraction of A means the number of moles of A divided by the total number of moles. This is the mole fraction of A. It is represented by Chi or Xa. We can use 2 or Chi or Xa. So if you want to find out the mole fraction of B, that will be Xb is equal to number of moles of B divided by total number of moles. So suppose if the solution is containing more than 2 or more than 3, suppose whatever the components, if you want to find out the mole fraction of a particular component, take the number of moles of that component, then divided by the total number of moles. That's it. Okay. So this is one example here. As we discussed now, the mole fraction of A in the solution will be the number of moles of A divided by total number of moles. That's it. Okay. Now coming to the molarity. So molarity means it is another important method to express the concentration. So molarity means it is the number of moles of the solute present in 1 liter of the solution. So here we have to find out the number of moles, that is moles of solute divided by volume of the solution in liter. Okay, so usually the unit will be molar. That is also important. Okay. Now, these are the important methods to express the concentration. We have molality as well. Molality will be the number of moles of the solute present in 1 kilogram of the solvent. This is here molarity means number of moles of solute divided by total volume of the solution. So molality, that is MO, that is will be here it is RITY, that will be LITY. Molality. Okay. So molality means it is the number of moles of solute present in 1 kilogram of the solvent. Okay. So number of moles of solute N divided by mass of the solvent. Mass of solvent in kilogram. That is molality. Okay. So this is the difference between molarity and molarity. In molarity, we are using the volume of the solution, and in molarity, we are using the mass of the solvent. Okay. Now another important rule from this chapter is, or another important law, that is dilution law. This is also important. Okay. So this is like when we dilute a solution with the solvent, the solute concentration remains constant. Right. So when you are adding a particular, means when you are adding water, means we are diluting a particular solution. It may be an aqueous solution or whatever. So we are adding the solvent, whatever the solvent you are used, you are adding the solvent, then the solute concentration will remain constant, right? So we can use this formula for the calculation. So usually this equation we are using in laboratory, like the titrations and everything, right? So this is also important. Okay, now we have one more thing, that is another important parameter, that is normality. Normality means we know what is molarity, what is molality, right? So coming to the normality, this is the number of equivalents divided by the volume of the solution. This is number of equivalents. In the former cases, it was number of moles, right? Number of moles per volume, number of moles per mass of the solvent. Here it is the number of equivalents. So number of equivalents divided by the volume of the solution is called normality. Okay. Now the important thing is we have different factors. I mean different methods to express the concentration, right? So among these all the different kind of methods, temperature has no effect on mass percentage, ppm, mole fraction, molality, but it will affect molarity and normality. This is important. If we change the temperature, it will not affect mass percentage, volume percentage, ppm, mole fraction or nothing. But it will affect the molarity and normality. Why? Because in molarity, in the previous session we said that the molarity is the number of moles of solute divided by the volume of the solution. Right? But molality means number of moles of solute divided by mass of the solvent. So the mass of the solvent cannot be changed by altering the temperature. Okay, but if you are coming to the molality, here we are using the volume of the solution, right? Molality is the number of moles of solute present in particular volume of the solution. So here volume of the solution will be affected by temperature. That is important because when temperature is increasing, the volume will change. Okay, so volume is changing means it will affect the molarity, because similar to normality. Normality is number of equivalents divided by volume of the solution. Molarity is number of moles divided by volume of the solution. So here the volume means the volume of the solution will change with temperature. So what will happen? The normality and molarity will also change. Okay. That is this is the things regarding the normality and molarity. So temperature is affecting the volume but not on the mass. Okay, that's it. Now the next one, coming to the different types of solutions. So before that, we have to know Raoult's law. So what is Raoult's law? According to, so we have to know the equation for Raoult's law, that is P is equal to PA plus PB. That is if you are mixing more than one, what is that, more than one gases or something mixtures, then the total pressure will be equal to the summation. That is called different, we know that is we can predict the pressure, total pressure. Okay, so if you come to the Raoult's law and we are coming to the ideal solutions, there is an importance for Raoult's law. Okay, so according to this Raoult's law, we can say PA is equal to P0A plus P0B. That is Dalton's law of partial pressure, right? That is the total pressure of the, suppose we have a mixture having more than two components. So the total pressure of the mixture will be the summation of the individual pressures. So here, if we know the Raoult's law, it will be PA is equal to P0A into XA. That is Raoult's law. PA is equal to P0A into XA. Similarly, the partial pressure PB means partial pressure of the other component B will be equal to P0B into XB. So this is similar to that of the Henry's law. As we all know, this is similar. But in the Henry's law, instead of this P0A and P0B, we have Henry's constant KH. But here we have the individual partial pressure. Okay, so this is the difference. And we have some solutions which obeys the Raoult's law, and we have the solutions which shows the positive and negative deviation from Raoult's law. So some examples also we have to know, because in exams they will ask like which among the following is showing the positive deviation from Raoult's law, or which among the following is showing negative deviation. So there is a chance. So we have to remember the examples of these solutions which shows the positive and negative deviation. Okay, that's it. Now the colligative property. So the colligative property means the properties of the solution which is depending on the number of particles or number of moles. That is called colligative property. So colligative properties are of different types. First one, relative lowering of vapor pressure, depression in freezing point, elevation in boiling point. All these we know, right? Then osmotic pressure. So here we have to know the equations, because when you add some solute into the pure solvent, the boiling point of the solvent will increases. That is called the elevation in boiling point, right? Similarly, if you add the solute, it will decreases. The freezing point will decreases. That is called depression in freezing point. So these equations we have to know. That is delta TF is equal to KF into M. Okay, delta TF is the change in temperature by the addition. So that will be depending on whatever the amount of the solute that you are added. And here we have the constant as well. Okay, and it's molar elevation constant, molar depression constant. Fine. So one more thing is this colligative property is depending totally on the number of moles. Okay. Then another property is osmotic pressure. Osmotic pressure means we have the equation osmotic pressure pi is equal to CRT. That is, C is the concentration, R is the gas constant, T is the temperature. This is also we have to know. Okay, so these are the different kind of equations for the colligative properties. Now we have to know the Van Hoff factor as well, because in Van Hoff factor, because there are some substances which undergo dissociation and association in solutions, right? So in those kind of situations, we have to include the Van Hoff factor as well. That's also important. So these equations are also important. Okay, this is the thing. Now the remaining thing here is the azeotrophs. So what do you mean by azeotropic mixture? Azeotropic mixture means it is a binary mixture that have means they will undergo boiling at a particular temperature, but at a particular composition only. That is important. So in NEET, they will ask those kind of questions as well. Which among the following is a example for azeotrope? So azeotropic mixtures means they will boil at a particular temperature in a particular composition. That is the thing. Because water has one particular boiling point, alcohol, suppose ethanol or methanol, they have their own boiling point, right? But at a particular composition, they both will boil at the same temperature, because water has 100 degree and the alcohol have another temperature. So there is no chance in which they both boils at same temperature, but at a particular composition they will. That composition is called azeotropic mixture. Okay. Now we have minimum boiling azeotropes and maximum boiling azeotropes. So we have to know some examples for the minimum and maximum boiling azeotropes as well. Okay. So what is the minimum boiling azeotropes? We know that positive deviation and negative deviations from Raoult's law, right? So the solutions which shows the positive deviation from Raoult's law will be the minimum boiling azeotropes. And the solutions which shows the maximum, the negative deviation from the Raoult's law will be the maximum boiling azeotropes. So these things also means some of the examples also we have to remember. Okay, now we are moving to the abnormal molar mass. So we discussed about the Van Hoff factor, right? So coming to the abnormal molar mass means due to the dissociation or the association of the particles, there will be a chance in which the substances will show some abnormality in their molecular mass, means molar mass. Okay, that is the electrolyte which undergo ionization in aqueous solution. What they will increase, like they will increase the number of particles, because when the dissociation is taking place or when the ionization is taking place, the number of particles will obviously increases, right? So it will affect the colligative properties, because colligative properties are completely depending on the number of moles. So in those cases, we have to calculate the abnormal, means it is not as much the predicted value. So it will change. That also we have to remember. Then one more thing is degree of dissociation alpha. So we have to know the equation to find out the degree of dissociation. That is another thing. So these are very, very important. Okay. So degree of dissociation we have that is I minus 1 divided by n minus 1. That is for solute dissociation or ionization. If you come to the solute association, the degree of dissociation will be different. Fine. So we have to know both equations. In case of dissociation, suppose if you are taking like some other compounds, suppose they are dissociating some ionic compounds. They are dissociating, the degree of ionization, how much they ionized, that is equal to I minus 1 divided by n minus 1. If you come to the association, because if you take some other compounds, they will undergo association and they will produce the macromolecules. So in case of this association, the degree of ionization will be equal to 1 minus I divided by 1 minus 1 by n. So these two equations are also important. Okay, and then there's the Van Hoff factor. Using the Van Hoff factor, we can write the relative lowering of vapor pressure as well. Usually, the relative lowering of vapor pressure was like, that is P0 minus P divided by P0, that is equal to X only. But if you are considering the Van Hoff factor, we have to multiply with I. Okay, so similarly in case of depression in freezing point, we know that delta TF, that is the depression, is equal to Kf into Em. But if you are considering the Van Hoff factor, that is in case of the compounds which undergo ionization or association, we have to consider the I value. So these are the modified equations by considering the association and dissociation. The one that we discussed before was for normal. So this is for the compounds which shows association and dissociation. That's it. Okay. So these are the important topics from this particular solutions, means particular chapter. Okay. Now we have to discuss the important questions from this solution chapter from the previous past papers. Okay. Before that, if you have any doubt in between, you can ask now. Otherwise, I will move to the questions. Okay, so here it is given that the mass of glucose required to dissolve to prepare 1 liter of its solution, which is isotonic with 15 gram per liter solution of urea, and we have to find out the mass. Okay, here glucose solution is prepared by adding like 1 liter of solution which is isotonic with 15. We have to find out the mass of glucose required. Which solution we are preparing here? We are preparing 1 liter of glucose solution which is isotonic. This is important. Isotonic. What is isotonic solution? Isotonic solution means they are having same pressure. Isotonic solutions are having same pressure. So here we have to find out the mass of glucose required to prepare 1 liter solution, but its pressure, osmotic pressure will be equal to the same pressure of 15 gram per liter solution of urea. So whatever the mass you are taking to prepare the glucose solution, it's no matter, doesn't matter, because their osmotic pressure should be equal to the solution of 15 gram per liter solution of urea in the same amount of 1 liter. Okay, so let us do this. So we have to use this isotonic term for the calculation, because for this solution of glucose and that of ammonia, we are having same osmotic pressure, right? So what is the equation to calculate the osmotic pressure? That is pi is equal to CRT, right? C is the concentration, R is the gas constant, and T is the temperature. So here both the solutions are having same osmotic pressure. That is called isotonic solution. Okay, so here I am taking the osmotic pressure of the glucose as pi 1, and that of the urea solution I am taking it as pi 2. Pi 1 and pi 2. So I can equate pi 1 that is equal to pi 2. Why? Because both are isotonic, right? Now we are taking the solution at same conditions. We are not changing the temperature. Okay, so T will be same for both the solutions. Then what about R? R is the gas constant, right? That is also not changing. So if you take these two solutions, which is the one and only one changing factor is the concentration. For both the solutions, the concentrations will be same, because here for urea I am taking 15 gram per solution, and for glucose we don't know. We have to find out the mass. So the concentration of the solutions will be same, but the gas constant and the temperature are the concentration will be different, but the gas constant and the temperature will be same. So for glucose, I am taking the concentration as C1, and for this urea, I am taking it as C2. Okay, so now I can substitute, right? So pi 1 I am writing as C1 RT. No need to take R1 T1, because R and T are common for both the solutions. So for the urea solution, I will take it as C2 RT. Okay, so I can cancel the value of RT both sides. So it will be C1 is equal to C2. Okay, it means the concentration is same, right? So in order to get the same concentration, what is the equation to find out the concentration? Concentration is equal to number of moles divided by volume, right? Concentration C is equal to N by V. So for the solution here, 1 liter of solution is preparing for urea, glucose, and for urea it is given that 15 gram per liter solution. 15 gram per liter means it is also 1 liter. So volume of the solution is also same. Okay, so I can write N1 by V is equal to N2 divided by V. V is also cancelled. Now I can write N1 is equal to N2. Means number of moles of urea is equal to number of moles of glucose. So what is the equation to find out the number of moles? That is equal to mass divided by molar mass. So what is the, in case of glucose, we don't know. We have to calculate it, right? So I'm taking the mass of urea as small letter m. Okay. And for the mass of mass of glucose, I am taking a small letter m, that I have to calculate. Mass of urea, it is already given here, that is 15. So I can equate this here. That is N1 is the number of moles of glucose. That will be the mass M divided by their molar mass. Molar mass of glucose we can calculate from this. How? Because here the atomic masses are given, and the molecular formula for glucose is C6H12O6. So we have to find out the molecular mass of glucose, that is 12 into 6 plus 12 plus 6 into 16, right? So it will be 180. Now coming to the urea the mass is given as 15, and using this values we can find out the molar mass, because molecular formula for urea is also given, NH3CONH2. So the molar mass, if you add them, it will be 60. So here we can find out the mass of glucose required to prepare the solution. That will be 180 divided by 4, that is equal to 45 grams. So from these options, the correct answer is option B. Okay, so this is how we are calculating the mass of glucose. So here the term which is given in between the question, that is isotonic, that is the key for this answer. Okay, that is important. Okay, so this is the first question. Now the second question. Okay, so coming to the next question, it is like a plot of osmotic pressure versus concentration in moles per liter for a solution gives a straight line with slope 25.73 liter per mole raised to minus 1. We have to find out the temperature at which the osmotic pressure measurement is done. Okay. So we have to find out the temperature, and it is given that a plot of osmotic pressure versus concentration is giving a straight line with a slope of 25.73. This is the key for our answer. Okay, and we have to calculate the temperature at which the osmotic pressure measurement is done. So from this question it is clear we have to use which equation? The osmotic pressure, that is pi is equal to CRT. This one we already discussed, right? Pi is equal to CRT. So in the curve between this osmotic pressure and concentration, so we are taking a plot of osmotic pressure versus concentration, means it will be a straight line. So it means the slope of this graph is 25.73. So the slope of the graph will be the value of RT. So that is 25.73. Okay. So this is the value RT is, that is the slope is actually the value of RT only. So that is equal to, we can say this t value. So we can equate this, that is RT is equal to 25.73. So we can find out the value of t, that is 25.73 divided by R, right? Just rearrange this equation. And the R value is given here, that is 0.083. So we can write 25.73 divided by 0.083. So if you calculate this value, it will be 310 Kelvin. Okay. But in these options, it is given in degrees Celsius only. So how will you convert it into degrees Celsius? So in order to convert degrees Celsius temperature into Kelvin, we have to add 273. So similarly, if you want to convert from Kelvin to degrees Celsius, just subtract 273. So the temperature will be equal to 310 minus 273, that is equal to 37 degrees Celsius. So the correct answer is option C. So coming to the next question, here we have two statements. That is, first statement is helium is used to dilute oxygen in diving apparatus. And the reason statement is given as helium has high solubility in oxygen. Okay, so based on these two statements, we have to predict the correct answer. Okay, so here let us see the statements first. Okay, what is the first statement? That is, helium is used to dilute oxygen in diving apparatus. That is true. Okay, so because helium gas is usually used in diving apparatus, that is perfectly true. Now coming to the reason, helium has high solubility in oxygen. This is not correct. This is a wrong statement, because helium is not that much soluble in oxygen. It is poorly soluble. It is like helium has a high solubility in oxygen, right? Actually, helium is so poorly soluble. That's why they are poorly soluble in blood. Okay, that's why it is utilized as a diluent for oxygen in modern diving equipment. So this second one is not the correct answer. Okay, so first statement is correct, second statement is not true. So if you come into the options, the first one is A is false, R is true. That is wrong. Coming to the second one, both A and R are true and R is the correct explanation for A. That is also wrong because there is no, we cannot say that this second one is the correct answer, right? So coming to the C, both A and R are true, R is not the correct, again incorrect. Coming to the last option, A is true but R is false. So this will be the correct answer. That is the first statement is the wrong statement. Second statement is the correct option. Okay, correct statement. So correct answer is option D. Now the next question. Which one is not correct mathematical equation for Dalton's law of partial pressure? And it is given that here the P is denoting the total pressure of gaseous mixture. Okay. So first of all, we have to know Dalton's law, right? So what is Dalton's law? Dalton's law of partial pressure means if you are taking a gaseous mixture containing the components 1, 2 and 3. We have 3 components, okay? So in this gaseous mixture, the total pressure of the mixture, P total will be equal to the summation of the partial pressures of the individual components. That is PT is equal to P1 plus P2 plus P3. This is actually Dalton's law of partial pressure. Okay, now let us see whether which among the following is correct regarding this given Dalton's law. Okay, see. So the first one, P is equal to N1 RT by V plus N2 RT by V plus N3 RT by V. This is actually another mathematical equation for Dalton's law, right? Because according to ideal gas equation, we have PV is equal to nRT, right? Now, if you rearrange this equation for P, it will be nRT divided by V. Okay. So if you take 3 components in this mixture, the number of moles will be different because volume will be same, and if you come into the temperature of the gaseous mixture will be same, and the gas constant R is also same, but the amount of these gases that you have taken will be different, so the number of moles will be also different. So I am taking the number of moles of the component 1 N1, 2 N2 and 3 N3. So we can rearrange this equation of the total pressure, that is N1 RT by V plus N2 RT by V plus N3 RT by V. Means this is same. So option A is the correct mathematics, means this is the same equation for Dalton's law of partial pressure. But they are asking for the incorrect option. So this is not the correct answer because this is an expression for Dalton's law. Okay. Now coming to the option B, here Pi is equal to the mole fraction times the partial pressure. Okay, so this is also correct, right? Because we know that P is the total pressure, right? And Pi is the individual pressure. So if you come into the partial pressure and if you come into the Dalton's equation, this is same. So option B is also another equation for Dalton's law of partial pressure. So this is also not the correct answer. Now we are coming to the option C. Here it is given that the Pi is equal to mole fraction times Pi0. Here P, this is not the correct one because it is given the Xi is the mole fraction of the gaseous mixture, Pi is the pressure of the ith gas in the pure state. But in the previous one, in option B, it is the partial pressure of the ith gas. That's it. That's it. But here it is in pure state. So this is not the correct explanation. This is not the correct one for Dalton's law because this option C denotes the Raoult's law, not the Dalton's law. So option C is the incorrect equation for Dalton's law of partial pressure. That will be the correct answer. Okay, now coming to the option D, as we discussed now, P1 plus P2 plus P3. This is the proper equation to show the Dalton's law. So this is also not the correct one. So the incorrect mathematical equation is the option C. Okay, that's it. Coming to the next question, in one molar solution that contains 0.5 moles of a solute, what is the amount of the solvent present? Okay, so it is given that one molar solution. So molar means here we have molality, not molarity. Molarity is the number of moles of solute present in 1 liter of the solution. But molality means this is the number of moles of solute present in 1 kilogram of the solvent, right? So if you come into the molality, that is, it is depending on the mass of the solvent, not the volume. So it is given that the molality is 1. Okay, so first of all, we can write the equation for molality. That is, molality is equal to number of moles of solute divided by the total volume of the solution. Sorry, the total mass of the solvent, that is in kilogram. Number of moles of solute divided by the mass of solvent in kilogram. Okay. So here now we can substitute, right? Because the number of moles is given as 0.5. Now we have to find out the mass of the solvent. So how can we write it? Here the molality is also given as 1 and it is containing 0.5 moles of the solute. So here we can write 1 is equal to the number of moles, that is 0.5 moles of solute. That is, molality is 1. So molality is 1. We will write it, molality is 1. The number of moles N is equal to 0.5. So 1 is equal to 0.5 divided by the mass of the solvent. That's what they are asking to find out, right? Now we can write the mass of the solvent will be equal to, mass of the solvent is equal to 0.5 divided by 1, that is 0.5 kilogram, right? Now we have to write the answers in grams actually. So if you come into the options, option B and D we can ignore. Why? Because here they are giving the volume of the solvent. But we know that molality is the number of moles of solute present in mass of the solvent, not the volume. So we can omit option B and D. Now our target is option A and C. So here it is in kilogram, but option A and C is in grams. If you convert the 0.5 grams into kilogram, it will be 500 grams, right? So the correct answer is option A. C is wrong because C is given as 1000 grams. So the correct answer is B. Sorry, the correct answer is A. 500 grams of solvent. B, C and D are wrong. Now coming to the next question, here it is given that the correct option for the value of vapor pressure of a solution at 45 degrees Celsius with benzene to obtain in molar ratio 3:2. Okay, so we have to find out the correct value for the vapor pressure of the solution. Okay, so it is given that the molar ratio is 3:2. Okay, so the values of the vapor pressures of benzene and octane are given separately. That is 280 mm of mercury and 420 mm of mercury, right? So it is given that we have to assume these gases are ideal gas. So no need to worry about other factors because they are acting as the ideal gas. Okay. So first we can write the vapor pressures of these individual components. Okay. So the vapor pressure of the benzene is, I'm writing here vapor pressure of benzene, that we can write from here, that is equal to 280 mm of mercury. Now coming to the next one, vapor pressure of octane, that is equal to 420 mm of mercury. Okay. Okay. Now, here the molar ratio. Molar ratio means it is the ratio between the number of moles, right? That is given as 3:2. So we can write the total number of moles will be 3 plus 2, right? Because the ratio is 3:2 means the total will be 3 plus 2 only. So the total number of moles is equal to 3 plus 2, that is 5. Okay, now we have the equation to calculate the total pressure, that is P total is equal to P0A into mole fraction of A plus P0B into mole fraction of B. So here A will be benzene and B will be octane. Okay, so by using this one, here P0A and P0A and P0B values are given, but the mole fractions are not given, but we can find the mole fraction because the molar ratio is given, that is 3 to 2. So if you find out the mole fraction of benzene, that is, I am taking the benzene as A and octane as B. Okay. So if I am finding out the mole fraction of benzene, that will be 3 divided by 5. Okay. And that of another one, that is B, will be 2 divided by 5. Okay. Now I can substitute for the value of P total, that is equal to 280 times, that is 280 is the uh, vapor pressure of benzene, right? So vapor pressure of benzene is 280, mole fraction is 3 by 5. So 280 times 3 by 5 plus 420 times 2 by 5, that will be 168 plus 168, the total will be 336 mm of mercury. So the correct answer is option D. Okay, this is how we are calculating the total pressure of the solution. Now coming to the next question. Here, the mixture, different kinds of mixtures are given. We have to select the one which shows the positive deviation from Raoult's law. This is what I told you at the beginning, means we have to know the examples for the solutions which shows the positive and negative deviations. Okay, so here we have 4 different kinds of mixtures. So from this we have to find out the one which shows the positive deviation. Okay, so here the one which shows this positive deviation will be the mixture of ethanol and acetone. So option C is the correct one. Okay, this one we have to, like, we have some of the examples we have to memorize. Then only we can write it properly. Like we can't spend more time for this kind of questions because this is not any calculation. This is just memorizing. So we have to feed some of the examples in our memory. Okay. Because why this ethanol and acetone are showing positive deviation? Let's come to that one. In pure ethanol solution, we know that there is a hydrogen bonding, intermolecular hydrogen bonding. So the ethanol molecules are held together by the strong hydrogen bonds. But when you add the acetone, it will disrupt the hydrogen bonding and they will interfere with the hydrogen bonding network, right? Because in ethanol, we can see that strong hydrogen bonds. So when you are adding acetone, they are disrupting these hydrogen bonds. Okay, so what will happen? The positive deviation, what do you mean by the positive deviation? Because when the vapor pressure of the solution is higher than that of the predicted by the Raoult's law, that is called, they will be they will be showing positive deviation. So the deviation happens because they are weakening the hydrogen bonds in the solution and more molecules will be escaping from the liquid phase, right? Because positive deviation means the vapor pressure of the solution will be greater than that we predicted by the Raoult's law. So vapor pressure increases means they should become easily volatile. So how they are becoming easily volatile? The interaction between the individual molecules will be comparatively weak. That's why they are easily escaping. So here in this ethanol acetone solution, the interaction between the ethanol and acetone will be weak. That's why they are showing the negative deviation. Okay, so this is the reason for the, so that's why they are showing the positive deviation. So positive deviation means this vapor pressure will be greater. So the interaction between the components is that much weaker. So they will easily escape. So the vapor pressure become higher. That's why they are showing the positive deviation. That is the correct answer. So C is the correct one. Okay. Now we have one more problem. That is the freezing point depression constant of benzene is given here, that is 5.12 Kelvin kilogram per mole. The freezing point depression for the solution of molality having 0.078 is containing a non-electrolyte solution in benzene. Okay, so here it is given that we have to find out the is depression in freezing point. The freezing point depression constant Kf value is given for benzene. Okay. And we have to find out the depression in freezing point, that is delta Tf we have to calculate. Okay. The molality of the solution is also given as 0.078 molar, and they are containing non-electrolyte solution in benzene. Okay, so first of all, we have to know the equation to calculate the depression in freezing point. When you are adding a non-volatile solute into a pure solvent, usually the boiling point of the solvent will increases and the freezing point will decreases. So here you are adding a non-volatile solute and the freezing point is decreasing. Okay, so we have the equation, that is delta Tf is equal to Kf times M. Here Kf is the freezing point depression constant, M is the molality. Okay, so here if you come to the Kf value, we have that value, that is 5.12. Kf value is given and molality is also given, that is 0.078. So we can substitute the values here, that is 5.12 times 0.078, that is equal to 0.399 Kelvin. But in this question it is given that the answer should be round off up to 2 decimal places. So we can simply write the value, that is equal to 0.40 Kelvin. Okay, so the correct answer will be option A. So this is a simple question. Like we can directly substitute the value and we can find out the answer. Okay, that's it. Okay, next question. If the molality of the dilute solutions is doubled, what will be the value of molar depression constant Kf? Okay, so we know that the relationship between the molality and the depression in freezing point, right? So the depression in freezing point Kf is given, means that is given that the value of molar depression constant we have to find out. The molality is double. First, let us write the relationship between the Kf and molality. So when you add a non-volatile solute to a pure solvent, the freezing point of the solution will decreases, the solvent will decreases. The depression in freezing point is equal to Kf times the molality, that is Kf times M, right? And we have the equation to find out the molality, that is the number of moles of solute, that is M is equal to number of moles of solute divided present in 1 kilogram of the solvent, not the volume, right? So that is equal to number of moles of solute divided by mass of the solvent. Okay. So what is given here? Here the molality of the dilute solutions is doubled. The value of molar depression constant will be what? Actually, the concentration of the solution is not affecting the molar depression constant because it is a constant value. It will affect only the solvent nature. It means for different solvents, there are different values for molar depression constant. That is for Kf. So this Kf is completely independent of the concentration of the solution. If the concentration is changing, that is if whether the solution is concentrated, diluted, doesn't matter. It will not affect the value of Kf because Kf is a constant that will be differ for different kind of solvents, not depending on the concentration of the solvent. Okay, so here means we can say if whether the molality of the solution, means if the solution is diluted or concentrated, the molality means that is the concentration of the solution is not affecting, means the Kf value will remain unchanged. So correct answer is option C. Next question, which of the following is depending on temperature? Okay, so while discussing about the important points from this chapter, I told you we have different methods to express the concentrations, right? Mass percentage, volume percentage, mass by volume percentage, different methods are there. So here we have to find out the one, different terms are here, means different methods for expressing the concentrations are here. We have to find out the one which is depending on temperature. Okay, so that time I told you, like if you come to the factors, molarity, mole fraction, weight percentage, everything, whatever the quantity is having the volume in the solution, means the volume in the equation, it will be affected by the temperature, because if you check the molarity is the number of moles of solute present in 1 liter of the solution. So we can write the molarity is equal to number of moles divided by volume of the solution in liter. So this is depending on the volume. But if you come to the mole fraction X, that is equal to the number of moles of one component divided by the total number of moles. Similarly, if you come to the weight percentage also, this is the mass of one component, that is mass percentage or weight percentage is equal to mass of one component divided by total mass times 100. Now coming to the molality, that is the number of moles of solute present in 1 kilogram of the solvent. Means here we have to consider the mass of the solvent. Right. So in all these four different factors, we can see only the molarity is depending on the volume of the solution. So the mass, number of moles, they will not be affected by the temperature, but volume of the solution will be affected by the temperature. It means the molarity will be also affected, but mole fraction, molality, weight percentage, they won't be affected by the temperature. So the correct answer is option A, molarity. So here we have to calculate the percentage of pyridine that forms the pyridinium ion in 0.1 molar aqueous pyridine solution. Okay, so in order to calculate the percentage of pyridine that forms the pyridinium ion, we have to use the equation for degree of dissociation, because the degree of dissociation means how much substance is undergoing dissociation. So when you add the pyridine in water, they will produce pyridinium ion, right? So it is given that the concentration, that is 0.1 molar, and what is the percentage of pyridine that forms the pyridinium ion, means what is the percentage of the pyridine that is undergoing dissociation. So in order to calculate that, we have to use the equation including the base dissociation constant of pyridine, because pyridine is a weak base, they will undergo partial dissociation. So we can take the value of Kb, base dissociation constant, will be equal to C alpha squared. Here C is the concentration, alpha is the degree of dissociation. Now we can rearrange this equation for the value of alpha, that is equal to Kb divided by C to the power 1 by 2, means square root of Kb by C, because alpha denotes how much pyridine is undergoing dissociation and how much is produced the pyridinium ion. So that's equal to Kb divided by C. Now we have to substitute the values to find out the alpha. So Kb value, that is 1.7 times 10 to the power negative 9, and the concentration is given here, that is 0.10. Okay, so now we can find out the value that will be equal to 1.3 times 10 to the power negative 4. But we need it in percentage. Okay, this is the degree of dissociation only. We have to calculate in percentage. So the percentage of degree of dissociation will be equal to the value that we obtained times 100, that is equal to 0.013 percentage. Means option D will be the correct one. Now the next question, of the following 0.1 molar aqueous solutions, which one will exhibit the largest freezing point depression? We have four different compounds, right? Potassium chloride, sodium chloride, aluminum sulfate and copper sulfate. So we know that the properties of a solution will be directly proportional to the number of particles, that is the colligative property. So we already discussed about the colligative properties, that is the properties depending on the number of particles. So coming to the colligative property, they are depending on the number of particles, means in all these cases we have to calculate the number of particles produced. If you consider potassium chloride, they will produce one K plus ion and one Cl minus ion. So that will be only 2. If you come to the option B, NaCl, they will produce Na plus and Cl minus in aqueous solution. That is again 2. If you come into aluminum sulfate, we know that they will produce total, means more ions, right? Because Al2, they are the ions which can produce more number of ions. So they will be having the highest value of freezing point depression. If you come into the Cu2 copper sulfate, they are also having less ions, because in Al2SO4 thrice they will produce 2 Al3 plus ions and 3SO4 2 minus ions. So total it will be 5. That's why they are showing. So this means the number of particles is directly proportional to the colligative property, because freezing point depression is a colligative property. So the largest deviation of this freezing point will be shown by the compound which has maximum number of particles. So that will be obviously aluminum sulfate, which can produce 5 particles. So that will be the correct answer. If you come into copper sulfate, they can also produce only 2, because one Cu2 plus ion and one SO4 2 minus ion, that is again 2. So the maximum will be for aluminum sulfate. So the correct answer is C. So this is all about the questions from this chapter, important questions. So in the next class, we will discuss about the questions from the next chapter, electrochemistry. So hope these questions are clear. We have discussed the questions till 2014. So hope this is clear. So see you next class. Bye.